finding 3.3 increasing and decreasing functions and the first derivative test are what we're going to be talking about. Essentially, we're heading into where we're going to be able to pretty accurately graph functions without our graphing calculator. So we'll do increasing, decreasing, we're going to do intercepts, we're going to do asymptotes, we're going to do something called concavity, where by the end product of it, we can hand sketch very accurate, even strange looking graphs based off the information we get. Okay, so first thing we're going to talk about is definitions of increasing and decreasing. A function is considered increasing that for any two input values, x sub 1 and x sub 2 in an interval, x sub 1 is smaller than x sub 2 is going to imply that f of x, the output, is less than that. So it's essentially saying if I have an x value and I have another x value, when I put in their y values, this guy is lower than this guy. Okay, so from left to right, my x value is small on the left and bigger on the right, and my height is also small on the bottom and big on the top. As you look at it left to right, it's going to go up. Okay, decreasing then does the opposite. If I have two x values, okay, and if from left to right, so I have an x value to the left and an x value to the right, but then their outputs, the left side is greater than the right side in that case. So you're always still looking left to right is what that x sub 1 less than x sub 2 means. But then when they put it in the f of x terminology, it's talking about the outputs and you're looking at your y values. Now we can actually test for increasing, decreasing using a couple different things. So if we have a function, it's continuous, again, meaning if I trace it, my pencil doesn't get picked up, on a closed interval AB, and it's differential, meaning I can take the derivative of it on open interval AB, we have these three things. If f prime of x is greater than 0, okay, so if that output is above 0 for all x values in the interval AB, then f is increasing on AB, okay, is what it's saying. So if the first derivative is positive, it must be increasing during an interval, okay? All right, so that kind of makes sense to me because if I have, say, a curvy graph, all right, and I'm looking at this being my slope of a tangent line, your slope is going to, wherever your slope is positive, it's got to be increasing. So picture this. If I have a slope here, okay, it's increasing, but notice my slope is positive. But if I do a slope here, it's decreasing, so my slope must be negative, okay? If my slope is equal to 0, we already know that. Slopes of zeros are horizontal tangents, so that means it's not changing at that point, all right? Let's try it. So we're going to find the open intervals for which a function is increasing or decreasing. The function we're going to do is x cubed minus 3 halves x squared. So based off this information, all of them are comparing that first derivative slope. So we need to look at our first derivative. F prime of x is equal to 3x squared minus 3 halves times 2 is just 3, so 3x. And we need to figure out where it's positive and where it's negative. So before I can find out where it's positive and where it's negative, I want to find out where it's 0, okay? And so I'll find out where it's 0. I can factor out an x, 3x, and I'll be left with x minus 1. Using my zero product property, I'll set 3x equal to 0 and solve it, and I get x is 0. And I'll set x minus 1 equal to 0 and solve it, and I'll get 1. And it's defined everywhere because it's continuous everywhere, so we don't have to worry about breaking it up or anything. So then what you're going to do is we know where it's 0. So I get a number line because I want to know where it's negative. And I go ahead and plot my 0 and my 1. And I'm going to put 0 on top because they're zeros. They're what makes the slope 0. Okay. And then I am going to be plugging in values to the left and in between and to the right. So a value to the left of -1 or 0 is -1. A value in between is 1/2. And a value to the right would be 2. You're going to plug these in to the original function. Okay. Because I want to, well, you're going to plug them into the first derivative. And then if we're looking for actual outputs. So plug into the first derivative is what we're going to do. So if I plug in -1, I would plug in here the factored form because it'll be easier to evaluate if you're doing mental math. If you're using a calculator, it probably is just as easy either way. But plug in -1 there. 3 times -1 is a negative number. I only really care about the signs is all we're looking at. Okay? And then if I plug in -1 into x minus 1, I'm going to have -1 minus 1, which is a negative number. So I have a negative number times a negative number. So this is a negative number. Negative outputs, okay, if you go back up here and look, okay, f prime of x is less than 0 here. Negative output means it's decreasing. So I go ahead and do a slanted down line to remind myself it's decreasing there. I'm going to go plug in 1/2 now. All right. Oh, actually, it should have been positive. Sorry, negative times negative is positive. Let me erase that. I said positive, but I didn't write it. Okay. So if it's positive, it's above 0. If we go back up here, above 0 means increasing. Okay. And then I'll plug in 1/2. 3 times 1/2 is a positive number. 1/2 minus 1, again, I'm plugging it in here. 1/2 minus 1 is a negative number. Positive times a negative is negative. So that is down. And then if I plug in 2, I have 3 times 2 is a positive number, and 2 minus 1 is a positive number. Positive times a number positive is positive, and so I have that. So you kind of see a general shape, like it's going to be increasing to the left of 0, decreasing between 0 and 1, and increasing to the right of 0. These numbers, this number, and this number, are numbers we chose. So they're not part of intervals. I could have chosen anything. Instead of -1, I could have chose -100. Instead of 1/2, I could have chose 1 over 1,000, just something in between 0 and 1. Instead of choosing 2, I could have chosen 50. And so those are relative. These numbers here, these affect the interval I'm using because they are actually solved zeros. We didn't pick those, we found those. So when I'm doing my interval, to the left of 0, so let's do our increasing. We're going to say find open intervals, increasing, decreasing. Okay, it is increasing from left of 0 until 0, where it then is a turning point. It's going to start decreasing. So that's an increasing, so negative infinity to the left of 0 and up to 0. It is increasing. It's increasing again over here, starting at 1 and heading to the right. So it's increasing from 1 to infinity. Decreasing is here, and if you notice, it starts at 0 and goes to 1, and we would have that as 0 to 1. So if we actually were to, if you put this in your graphing calculator and look at a graph, it looks something like this. So if you can look, and this is at 0, and this is at 1. So it is increasing from negative infinity up to the out to the input 0. You're talking about just x values. And then from the x value 0 to the x value 1, it's decreasing. And then from the x value 1 on and on, it's increasing. Okay. So you can sketch that if you want and look at that. So the first derivative test takes that and takes it a little bit farther. Okay, so first derivative tests help us find maximum minimums. What it says is if a function changes, if the slope changes from negative to positive at a certain point, so a turning point that we were talking about, there's going to be a relative minimum. Okay, so here's an example of that. It's going from negative, so decreasing, to increasing. You're looking again at the slopes. Then they're going to have some sort of minimum. Would you look? It is. And then if it says if you have it go from positive to negative, so increasing to decreasing, then you're going to have a maximum. If it's either both negative or both positive, then it's neither relative min or relative max. So like this case, this is increasing. This is a special point. It's a critical value, but it's not a max nor a min, which you've seen that happen. We've done some of our functions before where they weren't maximums and they weren't minimums whenever we were doing max and min, relative max and min. And same with this, decreasing, its slope is 0 at this point, but nothing, it didn't change from either side. So if we go back up to the one we did, okay, if you look, it went from increasing to decreasing. So we're going to have some sort of max. And it went from decreasing to increasing, so we're going to have some sort of min. That is what it's saying. So I can actually, without looking at the graph, know that there is a max at 0 based off of this number line here and a minimum at 1 because the slope changed from positive to negative and then negative to positive. And then we're going to practice that. All right. So we're going to find the relative extrema of the ordered pair, or not the ordered pair, of the function 1/2 x minus sine x on the interval 0 to 2 pi. So that unit circle is coming back around. So again, like I mentioned the other day in notes, if you're not very familiar with unit circle, you need to make yourself more familiar with that. Okay, I know it's been a while since you probably did that in Miss Porter's class, but it's really important for you to be reviewing that unit circle. Okay, so we need to look at our first derivative. It is called the first derivative test for a reason. The first derivative of 1/2 x is just 1/2, and the derivative of sine x is just cosine x. Okay, and we have to equal it to 0, because we need to figure out where it's equal to 0. I'm going to add cosine x to both sides so that I have 1/2 is equal to cosine x. So then I need to figure out on my unit circle, where is cosine, which is your x value, where is cosine equal to 1/2? Okay, so that I'm going to be thinking about, and it has to be anywhere between 0 and 2 pi, so we won't keep going around the circle, we'll only go through it one time. So 1/2 is your input, which means if you're looking at triangles, it's going to be the shorter input because it's either 1/2 or √3/2. In those combinations, 1/2 and √3/2 always go together. One will be your input, one will be your output. And so it's this type of triangle here where it's a 1/2 by √3/2. So this ordered pair is 1/2 comma √3/2. But for what input, for what angle is that the case is what you're looking at. And so for that angle, that's a pi over 3. So every angle like that where the x value is short is going to be important. So this one, and this one are going to be cases where you're going to have a 1/2. But we only need the positive 1/2. So there's no squaring. So I won't use this one or this one because they're negative 1/2, but I will need this one here. So I've got to figure out how to calculate that. Probably the easiest way is if you know that this is 3 pi over 2, this angle here, it is just 30 degrees more that direction. Okay, 30 degrees is pi over 6. So I'm going to do 3 pi over 2 plus pi over 6 to find that out. Okay. And so then when I do that, we need a common denominator. So I'll have 9 pi over 6 plus pi over 6. Is that right? And so I'll have 10 pi over 6, which is reduced 5 pi over 3. So when we solve this, we get x is equal to pi over 3 and 5 pi over 3. So then the next thing I want you to do is get in the habit, after you do that, you're going to do a number line, and you're going to have pi over 3 and 5 pi over 3. And it is always important, too, to make sure it exists everywhere. It needs to be continuous for these things to work. That is like the disclaimer at the beginning of all these theorems. Okay, we will show you at some point methods for when it's not. We're just not there yet. Okay. All right, so then I need to pick values to the left, in between, and to the right. So a value to the left of pi over 3, a good value there would be 0. Okay. A value in between it, well, there's lots of options, but I'd pick something that's going to be easy to plug into. If this is pi over 3 here on my unit circle, and this is 5 pi over 3, an easy value might be pi in between it. And then we can do 2 pi. So we can have something like that. All right, so we are plugging these in to the derivative. All right, and this is my derivative here. I would like to kind of write what we're doing, because at some point we do something called the second derivative test, and you have to use the first derivative to help you with it. So I like to label on my line what I'm going to plug into. If I plug in 0, I will have 1/2 minus cosine of 0. Cosine of 0, that's here. This ordered pair is 1, 0, cosine comma sine. So that's 1. So we have 1/2 minus 1, which is negative. So I'll do a negative, and I'll do a downward slant, a sloped line that's down. All right, now I'm going to plug in pi. And so we'll have 1/2 minus cosine of pi. Well, that is this ordered pair, negative 1 comma 0. Again, its cosine is your x value. So it's negative 1/2 minus negative 1. So that's going to be a positive number. And then I'll plug in 2 pi, and 2 pi and 0 are the same, so it's going to be negative. So if you notice, I'm decreasing from negative infinity to pi over 3. Okay, these actual values are what you use for your intervals. I didn't ask us for that, but it's important to talk about. It is increasing from pi over 3 to 5 pi over 3, and it's decreasing again from 5 pi over 3 to infinity. It goes on forever. It doesn't stop at just 2 pi, even though it's in that interval. If you're talking about the interval, you would stop it at 2 pi, and you would stop it at 0. But if you're talking about like globally all the way across, you would do that. So then it didn't ask, though, for increased decreasing. It asked for relative extrema. So on this interval, what's the max? What's the min? It's not a closed interval, so we don't, since this is not like this, we don't worry about the endpoints. Okay, so if it goes, and let's review back, if it goes from negative to positive, so down to up, you're going to have a minimum. If it goes from positive to negative, so from up to down, you're going to have a maximum. So let's look at that. You can kind of see the shape. Down to up is going to have me a minimum. Okay, if you kind of visualize something decreasing and then increasing. And then here we're going to have up to down makes a mountain, so maximum. So we have a minimum at the ordered pair, pi over 3, comma, and we'll have to find that output. And we have maximum at 5 pi over 3, comma, something. And then we have to find those actual values. You have to do f of pi over 3 and f of 5 pi over 3. So for actual ordered pairs, you have to plug into the original. If you're looking for a location on your graph, you're not going to plug into the derivative. You're going to plug it into the actual equation for your graph. And so we'll be plugging these in to the function above. All right. So they're not going to necessarily be pretty answers. I'll have 1/2 times pi over 3 is pi over 6. And then minus sine pi over 3. And sine pi over 3 is 3 over 2. So it's going to be some sort of ugly number like that. And we don't have to have that exact value. Let's see. I'll plug it in my calculator. So we'll have, where's my pi button? So pi over 3 times 1/2 minus sine pi over 3. Okay, so it's I didn't make these big enough. It's about negative 0.3423. All right, and then we'll go do the same thing. And I'm going to do 5 pi over 3. And then our maximum is 3.48402. Okay? So we have those ordered pairs as our answer. Same type of problem, so same process. So we're going to do our derivative. We're going to solve it. We're going to put on a number line. We're going to look where it's increasing, decreasing, so that we can determine where there is a maximum min. All right, so finding relative extrema. Here we go. So we need to look at our first derivative. Okay, and we need to take the derivative. We're going to chain rule this. So derivative of the outside is 2/3 x squared minus 4 to the 2/3 minus 1, so we'll have negative 1/3, times the derivative of the inside, which is 2x. Okay, I would simplify that a little bit. It'll make it a little bit easier to solve. And so I have that 3 on the bottom for my 2/3 fraction. I have my x squared minus 4 to the 1/3 because it had a negative exponent. Things with positive exponents go on top, which is a 2 times a 2x, and so I have 4x on top. And then I have to figure out where it's 0. So this is continuous in the original, so that's good. It is not continuous here, so we will have to test around where it's undefined. So let's go ahead and set it equal to 0. Fractions are only equal to 0 when numerators are equal to 0. So we'll do 4x equals 0, solve it, and I get x equals 0 as one of my critical values. But critical values are also where it's undefined. It's going to be undefined where the bottom is equal to 0 because it can't equal 0. So if I add 4 to both sides and square root, I get x can't be 2 or negative 2. And we will put all that on a number line because it can still increase up to a place where it doesn't exist, and it can still decrease up to a place where it doesn't exist. So at 0, it is actually 0, and then we have 2 and negative 2 to test around. Okay, and I don't put the little 0 above those because it doesn't exist there. So I need a value to the left of -2, so I'll pick -3. In between -2 and 0, so I'll pick -1. In between 0 and 2, so I'll pick 1. In between 2 and infinity, and I'll pick 3. Okay, and again, those are choices, which is why we don't use those in our answers. It's just a process helping us find us. So we are using the first derivative test. So I'm going to be plugging these test values, not -2, 0, 2. If you plug those in, you'll get 0. That's how we got them, or undefined. But we'll plug in -3, -1, 1, and 3 into our first derivative. And again, you're just looking for sign. You're not looking for the actual value. Okay, so I'm going to plug in -3 first. So if I plug in -3, the numerator is negative. If I plug in -3 in the bottom, okay, I'm going to have, looking here, -3 squared is 9. 9 minus 4 is positive. The cube root of that is still positive, times positive number is positive. So the top is negative, the bottom is positive. Negative divided by positive is negative. Okay. I'm going to do the same thing with -1. If it helps you to go find actual values, you're welcome to just plug in your calculator, but we just need the signs. So I'm plugging -1. My numerator is negative. I am plugging these in here, by the way. Plugging in my first derivative, simplified. It'll be easier there. So I plug in -1 in the top in the numerator. It is negative. I plug -1 in the bottom. Okay, -1 squared is 1, and 1 minus 4 is -3, and the cube root of negative number is negative times positive 3 is still negative. So we have a negative over a negative. So we're going to have a positive. And then I will plug in 1, and I will have a positive number on top and a negative number on bottom. So it's decreasing. And I will plug in 3, and I'll have a positive number on top, positive number on bottom. So it's positive. All right. So if we were doing intervals of increasing, decreasing, it is increasing from -infinity to -2. From -2 to 0, it's increasing. From 0 to 2, it's decreasing. And from 2 to infinity, it is increasing. Okay, it didn't ask that, but we're capable of doing that level of increasing and decreasing. I'll go ahead and write those down, actually, because I do think it's important. And I think your textbook on some problems will combine them. So we'll have 2 intervals that are increasing in this case and 2 intervals that are decreasing. So our increasing intervals, if you look, is from here to here. So -2 to 0, and from here to here. And so 2 to infinity. It is decreasing from here to here. So -infinity to -2. And it is also decreasing between 0 and 2. What that does is helps me with max and min. If it is going down and then going up, you have a min. If it is going up and then going down, you have a max. If it is going down and then going up, you have a min. So these are relative, so you can have more than one. So we have maximum at a certain place, and we have a minimum at another place. Okay, so my maximum is at 0, comma, I'll go plug in 0 to the original function. Okay, I'll get a decimal for that. So 0 squared minus 4 is -4. And then that 2/3 means it's squared and then cube root. So then I'll plug in, or I'll square the -4, which gives me 16. And then I will cube root that 16. Okay, so this means squared and then cube rooted. And so the cube root of 16, it has a perfect cube in it, in an 8. So it's 8 times 2. So it'll be 2 root 2. Okay, for that. Or you could do a decimal approximation for that. And then your minimum is at -2 comma something and 2 comma something. And these are not intervals. I know they look like intervals, but these are actual locations, ordered pairs. If I plug in -2, I get 4 minus 4. And so I actually get an output of 0. And then my other minimum is actually at 0 as well. Okay. All right, last one. Finding relative extrema of f of x. So we're going to do the same process. And we'll still do the increasing and decreasing because I think that'll help you guys in the long run. F prime of x is your first thing. This is a quotient, so we're going to have to do the quotient rule. So the quotient rule says if we have derivative or a division, we're going to do low d high minus high d low all over the square of what's below for a derivative, or it's the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So we will do the bottom derivative of the top minus the top times the derivative of the bottom all over the bottom squared. X squared squared is x to the fourth. Okay, so then I will simplify. I'll have 4x to the fifth minus 2x to the fifth minus 2x. Make sure this negative here in the middle, that it goes through that. Okay, we can simplify a little bit, all over x to the fourth, of course. And that will leave us with 2x to the fifth combined like terms minus 2x all over x to the fourth. Okay. All right, we can simplify it a little bit more. If you notice, everything has an x. So I can have 2x to the fourth. Let's go ahead and factor that 2x out since we have to use it. We're going to end up solving this eventually. So we'll have 2x to the fourth minus 1. If I factor out a 2 and I cancel an x in the bottom, and then I've canceled an x in the bottom, so I have x cubed. So it'll simplify like that. So now if we solve this, okay, I can factor the top even more. I'm going to move up to the right here. So I'll have 2x squared plus 1, x squared minus 1, all over x cubed equals 0. Okay, zero product property says I'll set each part of the product equals 0, so 2 equals 0, can't happen. X squared plus 1 equals 0. If I subtract 1 from both sides, I have a negative number, so if I square root it, I have an imaginary number. Grateful for calculus that we only deal with real numbers. Then x squared minus 1 equals 0 is x squared equals 1. And if I square root both sides, I get both positive and negative 1. I also have it places undefined. The bar at the bottom is equal to 0 at 0. And so I will plug in these three numbers onto my number line. So I have negative 1, 0, and 1. And these are where it actually was equal to 0 at. Okay. All right. So you can't have maximum minimums where functions are undefined. Okay. In the original. Okay, if it's undefined in the derivative, that's one thing, but it can't be undefined in the original. All right, so we will not have, in the original function, it still can't be 0. We will not have a maximum at 0. That's important to realize, is from the beginning, x can't be 0. Where if we look at this one, where we had undefined in our derivative, it didn't have any undefineds in the original function. Okay, so we'll pick numbers to the left, in between, and to the right. All right, and we are plugging these into our first derivative. Now, probably the smartest place to plug into your first derivative would either be this one here or this one here. And I'm going to plug it in, I think, to this one because I think it might be easier to do it mentally. Okay, I'm going to ignore the 2 multiplied to the front. It's not going to change signs. Again, we're just looking for positive and negatives. It has no effect on the sign. Okay, so if I plug in negative 2 and I do it to the 4th power, it's going to be positive 4. Minus 1 is still a positive number. If I plug in negative 2 and I cube it in the bottom, it's negative. Okay, so I have a positive over a negative, so this is negative. Now I'm going to go plug in negative 1/2. All right. So if I plug in negative 1/2 into the 4th power, it's going to be positive, but it's going to be a very small number. To the 4th power means it's multiplied to itself 4 times. So I have 1/2 times 1/2 times 1/2 times 1/2. So that's 1/16 minus 1. So that's negative. All right. And to the bottom, it's negative 1/2 cubed, so it's negative. So it's a negative over a negative, so we will have a positive. I will plug in 1/2 into the top, and I will have that 1/16 again, minus 1, so negative. But the bottom is positive because 1/2 cubed is positive. So I'll have a negative over a positive, so it's negative. And then I will plug in 2, and I will have 2 to the 4th power, which is a positive big number like 16. And then I will minus 1, and I'll have a positive number all over another positive number. So positive over positive is positive. So if we're doing intervals of increasing and decreasing, to help us out, it is increasing from negative 1 to 0, and it is also increasing from 1 to infinity. It is decreasing from negative infinity to 1, negative 1, and it is also decreasing from 0 to 1. Okay, none of those intervals should, I'm going to say overlap because none of the endpoints are included. They can't be the same interval overlap each other. Okay, they can share an endpoint, but they can't actually overlap. All right, so then if we're doing maximum, minimum, you're going to have maximums where it's going from increasing to decreasing. So there's a max here normally, but again, it can't be 0. So we're not going to have a max there. And so then we don't have any maximums. We have 2 minimums because it's going from decreasing to increasing, decreasing, increasing. Okay, there will not be a maximum at 0. That cannot happen. All right, so then we've got to plug in those values so that we can have correct answers. All right. So we will have no max, but minimum at -1 comma something and 1 comma something. And you plug those into the original because they're actual locations. So -1, plugging in here, -1 to the 4th power is 1, plus 1 is 2, all over -1 squared, which is 1. So we have 2 over 1, so it's just 2. I'm going to plug in 1, and I will have 1 plus 1 over 1. Okay, so 2. So there are your minimums, no maximums. All right, that is the end of our notes for today. Last notes until January.